Right. Okay. Right. The idea. Okay, we'll do a story. Right. Okay. Uh, now, mainly when we do these theories, also we understood that mostly we considered all the examples, all theories we explained based on the extension. So when you apply the external force, then that rod or that string or that spring undergoes kind of expansion, extension. But based on that only we did the theories. But remember, those stories are applicable when because of the applied force, if the rod or spring or string undergoes compression also, right? That's to also keep in your mind. Next story, a story like this. A story like this, right? So then we'll discuss, right? Uh, right. We'll do question number one, 19 into variables question, right? A rod AB of length L1 connected to another rod BC of length L2, and the combined rod is subjected to a fixed stretching force capital F as shown in the figure. If the both rods are identical, if the both rods have identical areas of cross section and the ratio Young's modulus of the material of the rod AB over Young's modulus of the material of the rod BC 2 to 3. The extension produced by the rod AB, the extension produced by the rod AB becomes equal to that produced by the BC when some stories. Okay. Okay. Now 99 to available. Question number one. 19 to available. Question number one. Right. Very important to remember now. Okay. Let's consider a rod. Okay. Now I explain some theory points and I just give an idea, right? Okay. Every question my target is to give you the theory more and more. So just consider there's a rod. So last I explained that. Last explained when you apply the external force on the rod. So when the rod undergoes a change in length, it can be a extension, it can be a compression. Last day I told you that we are assuming cross-sectional area of the rod remains constant. In the real scenario, obviously cross-sectional area changes. But what we do, we consider all the questions cross-sectional area remains same. Yeah, length maybe increases or length maybe decreases, but cross-sectional area remains constant, right? There's a rod, its cross-sectional area remains a constant. Cross-sectional area remains constant. Okay. So then, so when we apply an external force, we know that this rod undergoes kind of extension. Okay, I say that initially the natural length of the rod is like this. Initially, the natural length of the rod is simple something. Initially, okay, natural length is simple L something. So then this is simple L. So then this is the extension. Extension simply. If a change in simply, then initially the applied external force is 0. But when the extension is simply, we notice that at this instant, the applied external force is capital F. Then if you are marking the elastic force, I told you that every instant elastic force is exactly equal and opposite to the applied external force. That's what I taught you. I taught you. So if you are marking the elastic force, not important. Okay, right. What are the equations that we learned? We learned that Hooke's law under the proportional limit. Within the proportional limit, we can apply the Hooke's law. Within the proportional limit, we can apply the Hooke's law. Hooke's law means we know that F equals force constant into simple E. That is one equation. And also remember the next equation is F sigma equals. Now we know the stress means force over area, that idea. And strain means we know that strain means change in length over initial length, natural length, simple length. And the most important equation is stress is equal to Young's modulus, if elastic modulus into strain. Strain is the most important equation. From this equation only we derive that equation what uh, stress means F over A, Young's modulus, strain means E over A. That's it. So we can do any questions based on these few equations. We can discuss any few questions based on these few equations. Right. First important thing I want to tell you is remember when they talk about two or three different rods connected together. When they talk about two or three many rods connected to it together, then they can connect the rods, springs or strings either in series. If not, they can connect the rod strings either in parallel. So now I will tell you in this question, I will tell you when they connect in series, what to be remembered, right? Remember, if there are different rods connected in series, remember, right? Important story. Let's say now there are two or three rods. Now I explain considering two rods. When there are two rods connected in series, most they give the cross-sectional area of the rods are same. Most of the questions they say that cross-sectional area of the rods are same. Right? These are three different rods made with different materials. So then if they made with different materials, you know that. Now I told you that this Young's modulus, elastic modulus depends on the material. If they made with different materials, we know that. They are elastic modulus, Young's modulus are different. Right? Okay. Right? So remember, right? These two rods are made with different materials. So they have different Young's modulus, elastic modulus, Young's modulus Y1, if not E1. So this one's Young's modulus E2. Right, but both of them are having same cross-section area. Normally they give same cross-section area rods only. Both of them have same cross-section area when the rods are in series. When rods are connected in series. Next I will tell you what will happen when they connect in parallel. Okay. So when they are in series, and let's say when you apply a force. So when you apply force, remember, actually you're applying the force from the second rod, end of the second rod. So you're applying the force from the end of the second rod. But if the rods are in series, remember, the external force experienced by both the rods are equal to the applied force. If the rods are in series, the external force experienced, if not the elastic force experienced by both the rods are same. If. My important point is, right? The external force experienced by both the rods are same. Right? Write down. External force experienced by both rods are same. If. Write down. External force experienced by both rods are same. If. Right? The force is same. But remember, the force applied on both rods are same. If they are made with different materials, their extensions can be different. I can't exactly tell you their extensions are different sometimes based on these parameters, length and something. Their extensions can be same. Generally remember, when the rods are in series, the force acting on both rods are same. The external force acting on both rods are same. But remember, the corresponding extensions are different generally. The extensions are different. Right? So when you apply it, then both of them undergoes kind of extension. So this one's extension is different. This one's extension will be E2, right? I didn't draw after they extended. I didn't draw that diagram, but remember, force same. The external force, right, on the external force applied with rod sign series, the external force applied on each rod is same, but their corresponding extensions are different. But their corresponding extensions are different. That story. That story keep in your mind. But remember when the rod sign parallel, remember normally, right? The normal story. Just because there are two rods. There are two rods. But they are having now there are two rods. They are having same length. They are having same length. This story I will explain bit later. Bit later. Okay. This story right on. Okay, we'll go to the question now. Question. If you go to the question story, right. Then they mentioned there are two rods, lengths given as L1, L2, ABC. Right. There are two rods. I take this example. The point A, point B, and point C. Right. And length is L1. AB rod is having a length L1. And BC rod is having a length L2. This length is L1. This length is going to be L2. Right. Okay, no issues at all. I understand. Right. And the combined rod is subjected to a fixed stretching force of F as shown in the figure. If both rods have identical areas of cross section, both of them have same cross sectional area, capital A, capital A. Young's modulus of the material of rod AB. Let's say Young's modulus of rod AB is, I say, Young's modulus of rod AB I defined as E1. Young's modulus of rod, okay, Y1. Young's modulus of rod B is, let's say, Y2. So they mentioned that Y1 to Y2 ratio. Y1 to Y2 ratio, they have given AB to BC 203. So they have given that. Given data, Y1 to Y2 ratio is 203. This might be important. This might be important. This might be important. Right? And they're asking the extension produced by the rod AB becomes equal to that produced by BC. Very simple. Now they are telling very simple story. When you apply capital F external force, right? So in order to have now you know I told you that when you apply external force capital F, definitely if the rod sign series, each rod experience same capital F external force, that's 100% true. But generally, corresponding extensions different. The extension of rod A and the extension of rod B are different generally. But I told you that there are some instances based on the lengths and other parameters when the rod sign series extensions can be equal also. Now they are telling both of them experiencing FF external force and both of them have same extension. If I do the diagram for our understanding. If I do the diagram for our understanding. For understanding. Now learner. Now earlier the black color rod was somewhere here. But now it has extended. It has extended. Now the extension of this black color rod is, I mark it as simply extension of black color. The natural length is L1. The natural length is L1. Extension of the black color rod. You don't worry, I will teach you now. Now even though you didn't do questions yet, I will explain everything properly. You stay focused until 12:30. Somehow make yourself awake until 12:30. Extension of black color rod is, let's say, simply. Extension of black color rod is simply. And blue color rod also undergoes extension. Blue color rod also undergoes extension. Undergoes extension. So natural length is it's L2. Extension of blue color rod also simply. Extension of blue color rod also simply. Both of them experiencing same force. Right? Okay. This is the idea. Okay. So now what you can do now in this scenario with the rod sign series, what you can do, you can apply this equation. stress equals Young's modulus into strain. If not this equation, you can separately apply for each rod. Now apply this equation for rod, this black color rod 1. If you apply for the black color rod, that equation. So you can apply what equation? You can apply this one for this one. Normally, most of the time we apply this equation, right? So when you apply this equation, F of A equals, that means stress equals Young's modulus E over L. If you apply for the black color rod number 1, black F for rod number 1, black F for rod number 1. So then the force is force acting on the external force acting on the rod number 1. That is same as F. Cross sectional area is, let's say, capital E. So both of them have same cross sectional area, capital E. Cross sectional area is capital E, right? The Young's modulus of black color rod I defined as Y1. Then the E means extension. That is simply over natural length, initial length of the black color rod is L1. This is why write it as equation, let's say 2. So then what you can do, you can apply the same equation for the blue color rod, for the rod number 2. Black rod, if not blue rod number 2. Then the force acting on the blue color rod also same as F. I told you F. The area is same area A. Young's modulus of blue color rod is Y2. And the extension of the blue color rod is also same as E. Natural length of the blue color rod is L2. Equation 3. That's it. So if you divide equation 2 by 3, if you can equal, right? F over A, you can equal them. If you equal 2 equals 3, 2 equals 3. You can write down. You can write down what? You can write down Young's modulus Y1 E over L1 must be equal to Young's modulus Y2 E over L2. So then here we know that simply cancel out. They're asking us to find what in the question? In the question they are asking. L1. Subject L1. So when you subject L1, our L1 will be L1 equals Young's modulus Y1 over Y2. If you substitute L1, Y1 over Y2, L2. So Y1 over Y2 means we know. Y1 over Y2 means 2 to 3 ratio. 2 to 3. Y1 over Y2 means we know it's 2 over 3. It's 2 over 3. So then we can write down. Finally, so we can write down somewhere here. It's 2 over 3. So I write down here, it's Y1 over Y2 means we know it's 2 over 3. 2 over 3 L2. That's the answer. What is the answer? For that question, second one is the answer. Now learn from the questions you learn. Question number 1, answer is 2. Right. So the next story. The next story. I go randomly. Right. Right. We'll do question number 7. 19 and 11. Question number 7. 19 and 11. Question number 7. Nineteen, 11. Idea. What they're asking? They are telling that elastic string has a length 30 centimeter. When the tension on it is 3 Newton. See that sentence. Elastic string has a length of 30 centimeter when the tension on it is 3 Newton. If that string is having a tension means very clear that 30 centimeter is not its natural length. Correct me? Because we know that today also we learned in that previous session also we learned that if the string or spring or string, if the string or spring, right, if they are at the natural length, the tension is 0. If they has a tension, then that string or spring is not at its Natural length. That is the idea. So very clear. That means currently it is stretched. Elastic string has a length of 30 centimeter when the tension on it is 3 Newton. Right? Let's say this string is natural length is simple length. This string has a natural length simple length. This string has a natural length simple length. But the total length of the total length is how much? The total length, natural length is simple length. The total length is how much? 30 centimeters. It's 30. 30. Okay. Then what is the corresponding tension? The corresponding tension is the corresponding tension is the corresponding tension is how much? 3 Newton. Corresponding tension is 3 Newton. Right? The external force that you applied is 3 Newton. That's why corresponding tension on the string is 3 Newton. Right? That's the idea. The F is 3 Newton. Let's say F1 is 3 Newton. F1 is 3 Newton. So okay, right? Then we can remember this equation. F equals K equation we can remember. Right? Okay, next story. Next story. When the tension is 4 Newton, the length becomes 32. That's obviously I told you more the string that you extend, more the string, when you extend the string more and more and more, I told you that the corresponding, even the required external force, if not developed tension force, if not developed elastic force, is increasing, right? So when you apply 3 Newton, the tension inside the string is 3 Newton, the total length is 30 centimeter. If I'm extending more, now the length is 30. So the length is how much? The length is 32. Then the required force is 4 Newton. 4 Newton. Same string. So now the length is 32. Then the tension force in the string. That is how much, right? The external force that you applied. That is how much? 4 Newton. Right? So then what you can do? Natural length is how much? Natural length is simple lil. Natural length is simple lil. Now the length is 32 centimeters. 32 centimeters. Learn from stories. Learn from these questions. So then we want to find in the question the length of the string will be. I think we want to find with the tension is 7 Newton, the length. Okay. When the tension is 3 Newton, length is 30. The tension is 4 Newton, the length is 32. When the when the force is 7 Newton, what will be the what will be the length of the string? Very simple. Now you can do this question different way. There are different ways to do this question. So what you can do, one can find now based on this given data, we can remember F equals K equation. So one can easily find based on this given data, you can find K and you can find the K value. If you found the K value, thereafter you can easily do the remaining story. Right? Shall we apply this F equals K equation for the first scenario? Scenario one. Scenario one, if I apply the first equation, scenario one. Scenario one, we know that if we apply F equals KE, scenario one. Scenario. Right? F equals K equation. Then the force, external force applied on the string is the tension force. That is how much? That is going to be the 3 Newton. 3 Newton. Then the K value actually you don't know. That's K you don't know. The force constant of the spring you don't know. String you don't know. Extension, change in length. Natural length is simple lil, but now length is 30 centimeter. Then the extension will be how much? 30 minus simple lil. I convert 30 into meters. 0.3 minus simple lil, I don't know. I want to find K. If I find the K, I can find the remaining answers. equation simply. Scenario number 2. Scenario number 2, what you can do again, because you want to find K, but the problem is you don't know simple length. Natural length of the string you don't know. Again, what you do, scenario number 2, again you apply same equation, scenario. Then you understand that. Then the scenario number 2, the tension force acting on the string, the external force is 4 Newton, right? Then the spring constant is, force constant is K, and the extension, now the length is 32 centimeters, in which natural length is simple length, then the extension will be 0.32 minus 32 centimeters minus simple length. And then from these two equations you can find K as well as L. You can find both. Right? So there are two unknowns in one equation. There are two unknowns, two equations. You can find the answer K and L. Find the answer K and L. So what you can do, different ways are there. What you can do actually, if you want to find K, the best option is, if you want to find K directly, the best option is, the best option would be, right? The best option is, if you want to find K, you can subtract equation simple B minus equation simple A. Simple B minus simple A. That is one option, right? So then, yeah, then you can find K. Right? We'll do that. Equation simple B minus simple A. So then we are getting here 4 minus 3 means how much? 1. 1 equals, expand the bracket, simple B equation minus simple equation. 0.32 into K, 0.32 K minus KL. But I don't want to write like this. Minus KL. Then minus B minus A minus 0.3 K, 0.3 K minus KL, minus KL. Then you know that these two cancel out. Finally, you can find your minus minus plus, these two cancel out. Then you can write on 0.32 K minus 0.3 K means 0.02 K. So you are getting 1 equals 0.02 K. Finally, what is your K value? Finally, your K value will be 1 over 0.02. 1 over 0.02 means how much? 1 over 0.02. That means how much? 100 over 250. Am I correct? K is 50. What is the unit of force constant? Last day I told you. Force constant unit is how much? Newton per meter. Newton per meter. Right? Newton per meter. Right. If you know the K value, you can find the L also. If you find the K value, you can find the L also. Right? Right. Now, okay. Let's find the L also. Let's find the L also. If you find the L, now K is 50. If I take the equation 1, from equation simply, we can write down, now 3 equals, now K is 50. K is 50. K is 50. I move this K to the left side. Then 3 over 50 must be equal to 0.3 minus L. Minus L. Minus L. Minus L. Find the L value. Find the L value. Find the L value. Find the L value. If you find the L value. So then we know that here 3 over 50 means how much? 3 over 0.06, right? If I'm correct, check correctly. Yeah? Sometimes simplification, I can also do mistakes. Then here 3 over 5 means 0.6, 0.06. 0.06 must be equal to 0.3 minus L. Substitute 0.3 minus 0.06. L means, remember how much? L means 0.3 minus 0.06 means 0.24. Am I correct answer? L is 24 centimeters. 24 hands up. Hands up. How many of you agree with me? L is 0.24 meters answer. Same, right? Okay. Now we can find the answer. Now, if you know the L and K, direct substitution. They're asking what? They're asking when the tension is 7 Newton, what is the length of the string? That's what they're asking. They're asking the question. They're telling the length of the string will be when the tension is increased to 7 Newton. When the tension is 7 Newton, What is the extension? That's simple. That's simple. So they're asking the length. They ask the length. Okay. So what you can do here? Finally, finally, you can apply the same equation. F equals Ke. Now the force is how much? The force is 7 Newton. The force constant how much? That is 50. And the you can find the extension directly. If they're asking the length, they're asking the length, right? They're asking extension length. They're asking extension length. Actually, they're asking length. Length ni. The length ni. If you want to find the length means what? Okay, we'll find the extension first. Extension is how much? Extension equals the increase in length, the change in length. Extension is how much? 7 over 50. 7 over 50 means we know that. 7 over 50 means we know that. How much? Here, 1.2 ni. Ah, 1.2, 0.12, am I correct? 0.12. That means 12 centimeters. Natural length is 24 centimeter. The now length is 36. Am I correct? 0.12 meters. That means 12 centimeters. Natural length is how much? Natural length is how much? Natural length is 24 centimeter. Natural length is 24 centimeter. When you apply 7 Newton external force, extension, increase in length is how much? 12 centimeter. Okay. Natural length is, that is 24 centimeter. Natural length is 24 centimeter. And when you apply 7 Newton force, the extension, the increase in length will be how much? That is going to be 12 centimeter. Then what is the total length of the string? 24 plus 30, 24 plus 12 means 36 centimeters. Answer is 36 centimeters. Right. I think from these two questions also you got a good understanding. That question answer is how much? Second one. What is the right answer? This question answer. This question answer. Answer this question. This question answer is no answer like that. Oh god, no answer like that. Oh god, no answer like that. There is an answer. 12. That's an answer. 34 Newton, 32. If the tension is increased to 7 Newton, increase not by any, increase 7 Newton means, if I did I do any mistakes here? 3, 0.3 minus L, 32, 0.32 minus L, it's 4. Then if you subtract here, it's 1, 0.32 minus 0.3 means how much? 0.02, K is 50. When K is 50, L means what? Here, 305 means 0.6, 0.06. Then 0.3 minus L. L means 0.3 minus 0.06. That means 0.24 ni? Correct ni? 0.24. Then 0.24 is L. The extension is how much? 0. Extension is 7 over 50. Force is this one. Extension is 50. 7 over 50 means how much? Here. 1. Oh, okay. Here I made a mistake. 1.4. It's 1.4. If I do a mistake, tell me. 705 means how much here? 705 means here 1.4. 1.4 means 0.14. 14 centimeter. 14 centimeter. 38. That's an answer. Great. 38. Answer the second one. Nice question. Nice question. Then done. That is done. That is done. Okay. Shall we do the next question? Eighth one. One end of a metal wire of length capital L and cross-section area capital A is tied to the ceiling. The other end is connected to a massless spring of spring constant K. Massless spring of spring constant K. A body of mass impelled hangs from the free end of the spring. If the Young's modulus of the material of the wire is capital Y, the total extension of the system is 1911. 1911 story. Question number uh, 8. Question number 8. Idea. One end of a metal wire of length capital L, cross sectional area capital E is tied to a ceiling. Is tied to a ceiling. Is tied to a ceiling. Length is capital L, cross sectional area is capital E. Natural length, I think, maybe. Cross sectional area is capital E. The other end is connected to a spring or spring constant. Spring or spring constant K. Right? Okay. A spring. This one is having a spring constant K. Alright. A body of mass simple limb hangs from the free end of the spring. A mass is hanging. That means, so why they mentioned a mass, you want to understand that when you are hanging a mass at this end means basically you are providing an external force equal to simple mg at this end. You are providing an external force equal to simple mg at this end. So then you can mark the external force applied at the end of the spring is simple mg. Simple mg. Right? Okay. Okay, that is the idea. That is the idea. The Young's modulus of the material of the wire is capital Y. The Young's modulus of the material of the wire is capital Y. This one is capital Y. This is the wire, metal wire. It's a spring. Young's modulus of the metal wire is capital Y. The total extension of the system. The total extension of the system. Total extension. They're asking total increase in length. The total increase in length. Right? Very simple story. So then it seems like that two rods, if not two strings, two system connected in series, something like that. Then you know that I told you that in that scenario, the external force experienced by spring as well as this thin wire are same as mg. Right? When there are two rods in series, the external force experienced by each rod is same and equal to capital F. Same story is applicable in here also. Then you can tell that the external force experienced by the spring also mg, external force experienced by the wire also mg. They are asking the total extension. Then you want to find the, because of this mg external force acting on the wire, how much this wire has extended, extension of the wire plus because of the weight, how much spring has extended, extension of the spring. When you get the addition, that's the answer. We'll try to find it. Then we know that extension. I want to find E. So F over A means we know that Young's modulus Y E over L. It's the equation. The main equation is the main equation. Is the main equation. Is the main equation. Main equation. Right. The force is acting. The force acting on the wire is that is equal to mg weight. The force acting on the wire is external force acting on the wire is, and if they are series, mg cross-sectional area is capital E. Young's model is a given data. M is given data, G is given data, A is a given data. Young's model is given data. The wire. Therefore, I write down extension of the wire. Simply W. Extension of the wire, simply W. Natural length of the wire is capital L. If substitute EW. Substitute EW. Substitute EW, we are getting that. EW means what? MGL over. MG capital L over AY. Right? So this is the extension only from the wire. Likewise, find the extension from the spring. So what you can do for the spring, you don't want to apply this equation. If you want for the extension of the spring, what you can do, you can apply extension of the spring, you can apply this equation. For the spring, what you can do, for the spring, what you can do, you can apply F equals K. You can apply Hooke's law. But you want to assume that still, because of this weight, because of this external force, still the system hasn't reached their proportional limit. You want to think like that. Still, this weight is not sufficient to bring the system to their proportional limit. Then when you apply F equals K equation, F equals Ke equation, what you are getting? You are getting what? Give me a second. Write down. Write quickly. Write quickly. Quickly. Write quickly. Then you are getting what? F. F is what? The weight. Mg. F is mg. F is mg. And the force constant, spring constant is K. Simply means extension of the spring. Extension of the spring is, let's say, ES. S for spring. Then we substitute extension of spring, ES. Mg over K. Finally, the total extension means we can write down the total extension will be these two addition. So we have to write down E total. The total extension. E total means EW plus ES. That means NGL over AY. MG capital L. I write here. Okay, MG capital L over AY plus MG over K. MG over K, you can take MG as your common factor out also. If you take MG as your common factor out, you can write down L over AY plus 1 over K something. Are there any answer like this? Like this or like this, any answer? Are there any answer like this or like this? Any answer? L over YA 1 over K. Third one, is third one. It's third one, correct ni? Is correct ni? Third one, right? Done ni? Done. Story. Hands up up to now these ideas, these three MCQs. Crystal clear hands up. Now I think you get the idea. Elasticity, when you practice enough questions, it's not difficult. We'll do the essay questions also. We'll do date questions also. Thing is, hands up. Story is clear. Right, okay. Clear. Next story. Next story. Next story, then that is done. That is done. That is done. Right. Right. So then what else? So then right. Okay. Right. So we'll do 1990 question also. Sixth one. Sixth one. Six. The material of the human bone has a Young's modulus of 10 to the power 10 newtons per meter square. So we know that when you consider any material based on its properties, we defined a constant called Young's modulus. It depends on the material. So when you consider human bone, its Young's modulus is how much? 10 to the power 10 newtons per meter square, right? It fractures when the compressive strain exceeds 1%, right? The maximum load that can be sustained, by a bone of cross-sectional area this much, right? Not difficult. 1990 day level. question number 6 ni? 6. Right. Let's see now. This is our bone. Careful listen. This is our bone. I don't know like how to draw correctly. How to draw a bone? I don't know how to draw a bone. This is some kind of bone. I don't know. Right? It's a kind of bone. It can be leg bone or hand bone or whatever. Just think it's a uniform bone. Okay. Just one thing that it has a uniform cross section here. Think like that. If not, we can't do the question. Right? Okay. So then we know that because of the human weight, because when we are walking, you know that our entire body weight is acting on our leg bones. So simply it is like so we are this is if this is your leg bone, simply when the weight of the body acts on the legs of the bone, what's happening basically simply compressing the bone because of the weight, right? Because of the weight, it seems like applying a force on the bone and compressing the bone. That is some kind of idea. That is the idea. That is the idea. Okay. So think this is your bone for an example. Think your bone is some kind of cylindrical shape. Your bone is in the cylindrical shape. Think like that. Right. So then when you apply an external force, this time what's happening? This bone undergoes compression. Previous questions we talked about extension. Now we are talking about the opposite one, compression. Compression. Right. So then cross-sectional area is capital A. The cross-sectional area is capital A. So then we know that stress means we can define stress means what F over A. Strain means we know that strain means change in length over natural and the simple L. Let's say natural length of this, natural and the simple L. Natural and the simple L. Right. Now what you are doing, you are applying a, this is the natural length. That's the natural length of the bone is simple L, cross-sectional is capital E. So when you apply an external force capital F, and when you compress the bone, these are not important. This explanation is not important to get the answer. But I'm making you what? Familiar, these stories. So then you know that length of the bone has reduced. That means there is a change in length. There is a simply. The change in length is we call as what? The change in length, the reduced length. The reduced in this scenario, the change in length is a kind of reduced in the length, reduction in the length. That is we could name as the compression. That is we name as the compression. That is we name as the compression simply. Right? Then at this instant, the force acting on the bone is capital F. At this instant, the force acting on the bone perpendicular to the cross-sectional area is capital F. Is the idea. Okay, read the question. If you go to the question, now question they are telling, okay, they have given Young's modulus. If they have given the Young's modulus, definitely we won't deal with this equation. If they have given the Young's modulus, you won't deal with sigma equals Young's modulus into epsilon. If for F over A, Young's modulus into E over L. You want to use this equation, right? They have given Young's modulus, right? And they mentioned it fractures when the compressive strain exceeds 1%, right? So they are telling that when the compression is, right, sorry, give me 1 second. When the compressive strain exceeds 1%, right? They are telling this bone now you are compressing by pushing by applying an external force, you are compressing the bone. When you compress more and more and more, then we know that the strain also becomes high. When you apply more and more force, then it will compress more and more, and what will happen? The compressive strain also increases. Okay, what is the equation that we learned for the strain? Strain means change in length over natural length. We know that in this scenario, natural length is constant. Natural length is a constant. But we know that when you compress the bone, what will happen? The compression increases. As a result, strain increases. Compression increases, simply increases. As a result, strain increases. When the strain is remember 1%. When the strain is 1%. 1% means how do you write as a fraction format? The strain is 1% means the strain exceeds 1%. How do you write in uh, fraction format? 1% means when the strain is 1 over 100. They tell that when the strain is 1 over 100, the strain is 1 over 100. The strain is 1 over 100. They say that when the strain reaches 1 over 100, the strain is 1 over 100 to beyond 1 over 100, this bond undergoes fraction. Question they are asking the load, they are asking the force, right? So without fracturing the bond, that means maximum strain should be this 1 over 100, right? Then what is the corresponding force? The corresponding force, the force corresponding to a strain 1 over 100. Substitution. We know this equation. Right? F over A, Young's modulus, E over L. So we know this E over L is the strain. We know that E over L is the strain. Am I correct? Is a strain. Is a strain that is 1 over 100. Young's modulus how much? 10 to the power 10 is 1 over 100. Then the cross sectional area how much? The cross sectional area is given as how much? How much? 3 into 10 to the power minus 4. 3 into 10 to the power minus 4. So you want to find the corresponding force. So you want to find the force. What is the answer? When you substitute capital F, what is the answer? If you substitute capital F, the answer will be how much? 3 into 10 to the power 4 something. Am I correct? Hands up. I'm correct. Hands up. Answer is correct. Hands up. Hands up. The answer is correct. Hands up. The answer is correct. Right, is okay. Now I'm just giving some rough ideas. Okay. Likewise, we'll go to some statement questions. So we'll go to 2001 A level, question number 11. Question 11 story. Question number 11 story. Take a small break, not now, sometime later. 2001 A level, question number 11. 2001 A level, question number 11. Question number 11. Idea. There are 3 statements. Statement, a uniform elastic wire, suspended vertically from a ceiling, and mass is hung from the bottom in. A mass is hung, mass is a fixed mass. Now we can change the mass also. According to what they have mentioned, I feel like the mass is a constant. Mass is hung from the bottom end. Consider the following statements, assuming that the proportional limit of the wire is not exceeded. Still, that wire has not yet exceeded proportional limit. That means the force that you applied is not sufficient to reach the proportional limit. Okay, there's a wire hanged. Look at the idea. There's a wire. Even though I draw a very narrow, very thin wire, remember there's a cross-sectional area. There's a cross-sectional area, right? That is capital thing like that. And you hang the mass. You hang the mass means, remember, you have applied a constant external force. The external force that you applied is how much? The external force that you applied is how much? The external force that you applied is how much? The external force, when you hang the mass, the external force that you applied is simple mg. It's a constant. The external force you applied is a constant. Unless you don't change the mass. Now let's say earlier you hang 5 kilogram mass and now you're removing it and you are hanging another 10 kilogram mass. Then the external force that you applied is different. If you maintain the same mass, if you hang the same mass throughout the scenario, then the external force you applied is a constant. Capital F is a constant. Right? Can see shape ni capital F extension diagram. Naturally, the simple little. I do the diagrams again and again for our understanding. So when you draw diagrams and when we explain, we can understand, right? Okay. Now we'll try to understand the stories, what they are saying. Statement capitally, they are telling that, okay, If the length of the wire is doubled, the strain in the wire doubles. It's a natural length, simple length. Now we are going to increase your length to simple length. They are telling the strain will be doubled. We'll see. We'll see. If you know those equations, problem finished. If you know those equations, problem finished. The story. Okay, right. So we know that stress sigma equals Young's modulus strain. So they are talking something about strain. We know that for this wire, Young's modulus is a constant. For this wire, Young's modulus constant. Right? Young's modulus is a constant. Then this stress means what? We know stress means, we all know that stress means force over area. Right? Stress means I can write down the force over area, Young's modulus, and into strain. So as I explained already, Young's modulus is a constant. Then I said that since the same mass is hanged, your IP is a constant. Your cross-sectional area, I told you that all the scenarios, cross-sectional area doesn't change. If your cross-sectional area and the applied external force, Young's model is constant, then your strain must be constant. It doesn't matter you increase your length or you reduce your natural length or whatever. If the force across sectional area, Young's model remains constant, means remember, strain is constant. Strain is constant. So therefore remember, strain is constant. Statement capital A, they are telling that if the length of the wire is doubled, strain in the wire doubles. No. If you can maintain FA, Young's model is constant. Strain cannot be doubled. Strain don't become double, even though you double the length. Statement capital A is wrong. Learn important points. Statement capital A is wrong. Right. Statement capital B. What they ask you? Capital B statement. Idea. If the area of the cross section of the wire is doubled, the strain in the wire doubles. Again, same story. But this time they are telling that if the area is doubled, strain becomes double. That's wrong. Because F is a constant, Young's modulus is constant. This equation you can write down. Strain means you can write down from this equation F and Y constants, force and Young's modulus. Then strain means you can write down strain is inversely proportional to the area. So when you double the strain, when you double the area, when you double the cross-sectional area, remember, your strain will become half actually. Your strain will become half compared with the previous value. If the area of the cross-section of the wire is doubled, strain in the wire double is wrong. Strain in the wire becomes half. That's the previous value. Statement capital B is wrong. Last statement. Statement C. What are they asking? Statement C. If the hung mass is doubled, the strain in the wire doubles. Now we can say A is wrong, B is wrong. Then you can eliminate. You can get the answer A, B wrong means the only answer is C. Without discussing C also, you can get the answer is C. Or C says that if the hung mass is doubled, the strain in the wire doubles. That's correct. Why? Same equation. C, F is what? We know F is the external force that you applied. That external force that you applied is equal to the weight, simple mg. That F means what? Mg. F means mg over area, Young's modulus, strain. So you know that if you double the mass, see, G is a constant, Y is a constant, cross section is a constant. Then you can tell that Young's modulus directly proportional to what? The mass. When you double the mass, strain becomes doubles. That's correct. Therefore, right answer is third one. Story, right answer is third one. Next idea. Then that is done. Right. Question number 12. 12 story. 12 what they're asking. 12 they're asking that a mass is attached to a lower end of a vertical elastic string which is rigidly fixed at the other end. A mass is attached to the lower end of a vertical elastic string which is rigidly fixed at the other end. The mass is then moved down with a constant velocity by applying a force F. That story I will explain later. Constant velocity story. We'll talk about 14 and we'll try to come to 13. We'll go to 14 and we'll try to come to 13. Consider a situation where 14. Consider a situation where weights W are placed on vertical rods of radii R, 2R, 3R, 4R respectively. That means same weight, mg same weight is placed on different rods having different cross section areas. Those four, look at the size of the rods. They are having different cross section areas. First rod's radius is simple r, second rod radius is 2 simple r, 3 simple r, 4 respectively, and made of same material as shown in the figure. Those four rods are made with same material. Are they having same length? If the rods have same length and not attain the proportional limit, variation of the compression with the radius, variation of the compression with the radius is best represented by variation of the compression with the radius best represented. This question 2003 A level, 2003 A level story. I drove a rod. This story. Then we have a rod. Cross-sectional area of this rod is, let's say, capital E. Cross-sectional area of this rod is capital E. And the weight that you hanged, the weight that you place means when you are keeping a mass on top of that rod means you are applying a compression load. You are applying a compressive load. You are applying a kind of external force. That is equal to capital W. The external force that you applied is equal to capital W. Right. Let's say radius. Now, when you consider cross-sectional area, just think that these are cylindrical rods. These rods are cylindrical. The cross-sectional area I marked as capital A, corresponding radius. So, circular cross-section. Circular cross-sections correspond radius simple. Okay. Then if you apply now due to this capital W weight, it undergoes kind of compression simply, things like the simply compression. Then if you write the equation, what the equation? That F over A Young's modulus E over L equation. It's the only equation mainly we apply. F means the weight W, A means cross-sectional area. I can write it in terms of phi r square. Circular cross-section. Circular cross-section means I can modify this equation like this. I can modify the equation like this. I can modify the equation like this. F means W. W over cross-sectional area means phi r square. Cross-sectional area means phi r squared equals to Young's modulus Y. Young's modulus Y. They're asking extension. The delta L means change in length. Delta L means extension. Delta L means extension. E is delta L. They have considered E as delta L. So E over natural length is same simple L. From this equation, very clear that W constant, Y constant, Young's modulus. Initial length is constant for all the rods, and the pi is constant. Then you can tell that the change in length E, if not delta L, E is delta L. Right? Different symbols. That is proportional to 1 over r squared. That is proportional to 1 over r squared. So that is the idea. When the radius increases, when the radius increases, the idea is when the radius increases, remember the extension, the change in length drastically decreases. Are there any linear relationship between them? When r increases, let's say your y-axis r, sorry, your x-axis r, your y-axis, let's say extension delta L, if not E, then when the radius increases, extension, change in length decreases. Are there linear relationship? No, right? Why? E is proportional to 1 over r squared. Whenever the term comes squared, it's a curvy graph. It's a curvy graph, some kind of graph like this. Any graph like that? Are there any graphs? Tell me. Any graph? Any graph? First one. Check. First one is the answer. First one is the answer. Right. Okay. Right. So we do 15. 15. 2003, 14. 2003, 14. Next one, 15. Next story. Next one is 2004, 15. 2004, A level 15. Idea. Again, the statement question. Statement question. Stay focused. Stay focused somehow. Stay focused. The force required to increase the length of an elastic string by a unit length. What they're telling? The force required to increase the length of an elastic string by a unit length is given by K. Considering the following statements made about K. Consider the statements made about K. They have given three statements. Look here. Now, what is force constant? You can remember this equation F equals Ke. F equals K equation. K is force constant equals spring constant. Subject K. K means what? K means F over E. Can you define what is K? Force constant means what? The required force to have a unit extension. What is K? In order to have a unit extension or unit compression, the required force, the force per unit length, the force required for unit extension. That is K. That is K. Okay, now they are asking, consider the following statements made about K, made about the force constant. Now they have given three statements A, B, C. Three statements A, B, C. Let's see statement A. Statement A. So redo these questions again, once again, before you sleep. Redo it. Write down everything somewhere else, write down. Then when you practice properly, in case if your exam this paper question comes, let's go. Statement A. The value of K can be increased. The value of K can be increased by increasing the Young's modulus of the material of the string. The value of the K can be increased by increasing the Young's modulus of the material of the string. Right? Okay, just try to understand. Okay, I can remember that equation. This equation, the normal equation. F over E means Young's modulus E over L. Right? And we know that this F is Ke. I can write down F as what? Ke. I can write down this F means what? Ke. Ke over cross sectional area is A. Young's modulus Y E over N. This C cancel out. Then by substitute K, I can write down K as what? It seemed like K means YA over L. K means what? Y A over L. Y A over L. What they ask in this question? Give me a second. Question what they're asking. Question they are asking. Right. Okay. The value of K can be increased by increase the Young's modulus. That means you want to internally change the material. If you can internally change the material and if you can increase the Y, yes, you can change k. If you can do some kind of composition in the material, you can mix something, and you can like how we make the concrete strong. Likewise, you can mix something and you can change the internal molecular level, molecular bonds and everything. And if you can change your y, yes, you can change your k. Therefore, statement capital is correct. Right. Statement capital B, the value of k can be increased by increasing cross-sectional area of the string. The value of k, the value of k, the spring constant, the force constant can be increased by increasing the cross-sectional area of the string. Yes, k depends on cross-sectional area. When you increase the cross-sectional area, yes, you can increase your value of k. Statement B also correct. The value of k can be increased by decrease the length of the string. Correct me? When you reduce the length of the string, if you decrease simple lil, yes, k will be increased. Correct me? All three statements are correct. Answer is fine. How many questions we discussed so far? How many discussed? So far we discussed. Tell me. We'll take a small break. Discussed how many? How many discussed so far? Seven. Still seven. Eh? That's okay. We'll do a bit late. We'll do until the late night. Seven. Eh? So we'll take a small break. A 10-minute break. Now 11:33. 11. Come at 11:45. A small break. Come with a fresh feeling. Huh? 11:45. Take a break and come. That means Yes, right. So we'll come back. Story. And there are some easy questions at last. So then we can discuss question number 37, 36, 35. 35. Very simple. 35 story. 2021. 35. 2021 A level. Question number 35. Ne? Question number 35. Right. Idea. That is very easy. Very basic question. So they're asking that which of the following pairs of physical quantities have the same dimensions? Stress strain, we know that stress has a dimension ml minus 1 t minus 2. Strain have no dimensions. Work and energy. I think answer is following pairs of physical quantities have same dimension. I don't know why they have put this question in this section. Question number 35, I think answer is to work and energy have same dimensions, right? Yes, second one is the answer. 35, answer is second one. Question number 36. We'll go to 36. 36 is something very similar to the question, this question. 36 is something very similar to the question number 6. 36, 2021, 36. Next question. Next question. Two thousand 36. 2021 A level question number 36. Idea. Right. Then here they are saying that breaking strain of an aluminum rod is 0.2%. Now here it was given as 1% something. Now in it is given as breaking strain of an aluminum of a rod is 0.2%. What is the minimum cross-sectional area of the rod to withstand a force? This much. Now here they have given all the data and we want to find the force. Now the same story, we want to find the cross-section area. Same story. I'm not explaining anything. Same story. F4A, same equation. F4A, Young's modulus Y, E over L. E over L. This idea. Then E over L is, we know that is the strain. E over L is, that is the strain. Extension over natural length is our strain. Then F4A, right? F4A equals Young's modulus Y. Substitution. You want to find capital E? So you want to find capital E. So you want to find capital E. Right. Given F is how much? 3.5 into 10 to the power 3. 3.5 into 10 to the power 3. F is 3.5 into 10 to the power 3. So I want to find actually capital E. That's my target. Finding capital E is my target. Young's modulus how much? The Young's modulus is how much? Young's modulus of aluminium 7 into 10 to the power 10. 7 into 10 to the power 10. What is the strain? Strain is how much? 0.2%. You don't put 0.2 like this. 0.2% means 0.200. If you just put 0.2 wrong, they have given the strain as a percentage. But you want to write that strain as a fraction. 0.200. So very simplified, what will be the answer? Subject capital E. Subject capital E, what will be your answer? Subject capital E, what will be your answer? Your answer will be capital E is how much? If you simplified, capital E means how much? Capital E means here how much here? Subject capital E, 3.5 into 10 to the power 5 over 3.5 to the power 5 over 7 into 0.2 into 10 to the power 10. Right here it's 0.5. 0.5 over 0.2 means 2.5 into 10 to the power minus 5 something. Any answer to this? Just check with this. Any answer to this? Capital E. Clearly, that story I don't explain. Similar question already we have done. Similar question. Question number 36 also discussed. Last one, 37. So therefore, question number 36 answer is fourth one. 36 answer is fourth one. Then we'll go to question number 37. 37, 2022 A level. 2022 A level. 37. Idea. Three statement questions. Statement questions. Statement capital A, capital B, capital C. Now remember, Young's modulus is a property of a material. Remember, Young's modulus means a kind of property of a material. That's like a property that we have now. We have different qualities. Just because we wear different dresses, our qualities won't change. Same story. The Young's modulus of the material of a wire depends on statement A, the initial length of the wire. That's wrong. Even though whatever the length when you take, any length of the wire, the Young's modulus is going to be same. 1 meter long aluminium wire or 2 meter long aluminium wire or 3 meter long aluminium wire. The Young's modulus for all those wires having different lengths are same. Same Young's modulus. So therefore statement A wrong. Cross-sectional area of the wire statement B also wrong. Nature of the material C is correct. Therefore it answer C. Okay. Right. Right. So therefore, statement A and statement B wrong. Statement C is correct. So therefore, what is the right answer? Question number 36, right answer. 36 right answer will be what? 36 right answer will be only C, I think. Third one is the answer. The third one is the answer. That story done. So then we'll go to next question. Next story. Next story. Next story. Very simple ideas. Now, can you remember yesterday I told you that that strain energy, if not the elastic potential energy, then I taught you that strain energy per unit volume, that stories, right? You can remember, right? How I derived that strain energy equation. Strain energy equation, if you can remember. Look here, the next story. Next story. The next story. The next idea. Next idea, 2000. Let's see this question. Question number 33, 2019 level. Nice question. 2019 level. Question number 33. Right? Stay focused. Difficult, tired, what to do. So I'm the one who is having more tired than you. Right? Can you remember? Okay, look here. Now, the strain energy equation. Strain energy equation, if you can remember how I derived. Strain energy means we wrote something like the strain energy equals. I wrote half F simply something. This is the equation for strain energy. Strain energy per unit volume means something different story. Strain energy is the equation. Can you remember how did I derive this equation? I considered a rod that is at a natural length. Simply. Then I explained that if the rod is at the natural length, the force acting, there isn't any external force acting on the rod, therefore zero. Then I said that, let's say that when you apply capital F external force, I told you that, then the corresponding extension is I considered as simply. Corresponding extension we consider as simply. Right? So then I told you that in order to extend the rod, we have to do a work done. In order to extend the rod, we have to do a work done. The work done is storing as the energy inside the rod. That is we call as elastic potential energy, if not strain energy. The work done that we do in the attempt of extending the rod, storing as the energy inside the rod, that is we call as elastic potential energy, if not strain energy. Okay, that's what I explained. So then I told you that during this period, when the rod is extending, the force is varying. In that case, we have to go for an average force. I told you to define work done. What is work done? Work done means we all know that work done means force into displacement. Mechanics equation. Force displacement is mechanics equation. Right? So then we noticed in this scenario, the force that you apply is fluctuating from 0 to capital F. 0 to capital F. So therefore, what is the average force? 0 plus capital F over 2 is the average force. and the increase in length extension is simple E. From this only we derive the equation strain energy equals half Fe. Now this question also very same question. The next question 33 also very same. Right? They are telling when the tension of a wire is slowly increased from T1 to T2. Same story. Same story. Same story. But already in the initially already this wire has undergone kind of tension. There is a kind of external force acting on the wire. Now here initially wire is a natural length. So therefore the external force applied on the wire in the beginning is zero. But here in the beginning there is a external force. There's external force T1. In the corresponding extension, in the corresponding the length changes from L1 to L2. So they have the total length, not extension is given, total length is given. Initial length is L1 of the entire wire. So when the tension is T2, when you increase the tension force from T1 to T2, okay, now the tension is T2 because T2 is larger than T1. Then the total length of the wire is given as L2. If I ask you, when you are increase the tension force from T1 to T2, when you are increase the tension force from T1 to T2, right? If you increase the tension force from T1 to T2, during that period, during the time period, during the time period, what is the increase in length? What is the extension? What is the extension of the rod when the tension is increased from T1 to T2? What is the extension? That is this one. Correct me? How do you find this simply? Simply means L2 minus L1. Simply means L2 minus L1. That's it. L2 minus L1. What is the average force acted on the rod during this period? Average. Initial force is 0 earlier in this scenario. Finally safe. In here, initial force is T1, final is T2. Average means what? Average force means what? Average force means what? Average force is what? T1 plus T2. T1 plus T2 over 2. This is the average force into extension how much? Extension L2 minus L1. So they're asking what? So the energy stored means this work done. The energy stored means the work done. This story is clear answer. This question is clear answer. Nice question. Answer. This idea is very clear answer. This idea is very clear answer. This idea is very clear answer. Very clear answer. Very clear. Right? So very clear. That story also done. That story also done. Similar question was there. 25. Similar question 25. 2012 level. 2012 level. 25. 2012 level 25. 2012 level. Question number 25. Idea. This question idea. Whew. What a day. Right. Read the question. Read the question. Idea. This idea. What they're asking. Minimum amount of work that has to be done in order to fix a light elastic string of initial length L naught between two parallel with separated by a distance simple D, the tension T. Same story. Now they are telling that there is a wire, right? There is a wire string. That's a string. That's a string. Initial length is simple L. Natural length is simple L. So you want to extend this string to a length simple T. They mention simple T is larger than L naught. They mention simple T. Final length is larger than L naught. What is the now length of the string? That is simple D. If I ask you, what is the extension? The extension? Simple D minus simple L naught. The increase in length? Simple D minus L naught. Simple D minus L naught. Right? Simple D minus L naught is the extension. Clearly? Then in the beginning, there wasn't any forces. In the beginning, the string was under its natural length. Therefore, the force was 0 in the beginning. Right? Uh, at this instant, when the length is simple D, they are mentioning tension is T. Or the tension is T. They are asking minimum energy required, minimum work done. Minimum work done means strain energy. Average force into extension. What is the average force? Average force is what? 0 plus T over 2. 0 plus T over 2 means what? It's T over 2. Average force means 0 plus T over 2 into the extension. T minus L naught. What is the answer? What is the answer? What is the answer? What is the answer? I think first one. T over 2 D minus L naught. I think answer is first one. Answer is first one. First one. Answer is first one. Right. What else? Next story. How many we discussed so far? How many questions we discussed so far? How many questions we discussed so far? Mm, 12. Only 12. Why only 12? 13, 12. Only 12. Why, man? Right. Then what? Mm, oh. Okay. So then we'll do question number 10. 10th one, then 5. 10, 5. Question number 10. Now, can you remember the last theory I taught you? The last theory. So when a rod is trapped in between two vertical walls, when you increase the temperature, in the event if the rod is not able to expand, there will be a developed stress on the rod. Right? That story. That story. That story idea. That story idea. Right? That story idea. That story idea. The story idea. 2011. This is the question. Now I remember that equation. I defined that F equals what? AE alpha to theta. Right? That develops stress on the rod is AE alpha to theta. That equation, right? Okay. 2011. With the question. Question number 10. 2000. 2011. Question number 10. Idea. Read the question. With the question. They are saying aluminium Young's modulus 7 into and about 10 units per meter square. Linear expansivity 2.5 into 10 to the power minus 5 per Kelvin. Cylinder A, length 10 centimeter. Aluminium cylinder. Aluminium rod. Cross-sectional area 20 centimeters square is to be used as a space between two rigid walls as shown in the figure. At 30 degrees Celsius, it just slips in between the walls. They are telling why they meant it just slips between the walls. That means they want to let us know that initial length of the initially that cylinder, that rod is under its natural length. It is undergoing deformation, right? So when the temperature increased to 34, initial temperature is 30, when the temperature rise to 34, delta theta is 4 degrees Celsius. The force exerted by the cylinder on each wall. Cylinder produces force on the wall produces force on the cylinder. Yesterday I taught you the idea. The equation, direct substitution. Not to explain. Yesterday I explained the story properly. F equals, if I can remember, AE alpha delta theta, right? This is the equation, I think. Cross-section area is how much? Substitution. Cross-section area is how much? Cross-section area is how much? That's 20 centimeters squared. 20 centimeters squared. 20 centimeters squared, centimeters squared multiplied by 10 to the power minus 4. Young's modulus is how much? Young's modulus. Young's modulus is how much? 7 into 10 to the power 10. 7 into 10 to the power 10. 7 into 10 to the power 10. Linear expansivity. Linear expansivity, we know that. 2.5 into 10 to the power minus 5. 2.5 into 10 to the power minus 5. Change in temperature. 34 to 30 to 34. 4 degrees Celsius. Find the answer. Substitute to get the answer. Substitute to get the answer. You substitute to get the answer. Right. Question number 20. Same story. 2018 level, same story. A steel. Young's modulus, linear expansivity, beam of cross-sectional area, planned between two concrete supports as shown in the basic figure. I explained yesterday. The temperature of the beam rises delta T. The force that must be exerted by the concrete supports to each beam in order to keep the beam without expanding given by the same story. EA alpha theta. EA alpha theta. They are asking that force. EA alpha theta. First one is the answer. 2080 level. Someone simplified tell me the answer. This one. 2080 level. Next story. C. Not difficult. Right? Not difficult. If you practice enough questions. Question number what? 20. First one is the answer. Again, just refer yesterday's note and again read these questions again. Then you feel like this is very easy. And this Sunday we are planning the remaining MCQs and essays. Essays we are planning mainly. I'm planning essays at least 3-4 essays, and want to do remaining also. The time we have to find the time. Right? We have to find the time. That's the thing. We have to find the time. That's the thing. Time is the problem. What else? Tell me what else. This one. I think 24 is the same, ne? 24 see the idea. Figure shows as iron wire fast into a brass frame. 24, same story. Iron wire fast into a brass frame at room temperature. The wire is neither slack no under stress. They are telling initially it's at natural length, okay. Daily expansivity of the brass and iron are this much. Young's modulus this much. Right. That story we want to talk about, we want to learn about expansion of both the brass and the iron. That story I will explain next day. Next day I will explain. But there are some good questions also there. Right. 12, 10. Okay. Right. How many questions so far? So far? Up now so far how many? Bad, ne? So far how many, madam? She's paining. Only 40. Why? Why? Not even 15. I don't know why. I don't know why. Right. Answer of the session is very effective answer. Session is very effective answer. Right. Okay. So then again, then tomorrow, Thursday, tomorrow we are doing that heat practical discussion. Then tomorrow there's a paper class, paper writing also there tomorrow. 4 months to go. Then what? Then Friday, what Friday? Friday, I can't remember what I put in the schedule. So try to achieve the schedule as much as possible, right? Okay. So better, I like to do more things, but if you first thing is run support is important. Second thing is we should be in the time also. Okay. I think I'm doing my everything from possible in my end. Right. We'll see. Right then. So once again, review these questions and try the remaining past papers also. The remaining past papers will see now. Now we'll do your questions also. Review the past papers also. This is the idea. This is the oral elasticity. They can't ask questions beyond this. If we discuss the remaining stories also next day along with the essay questions, you understand now this is not a big story. Okay, right. Then next week we're going to start surface tension. Next day we're going to start viscosity, and the next week we're going to start surface tension. Want to finish unit 6 and 10 this month immediately. Then unit 7 and 11 next month. Electronics is there. Therefore, again tight schedule. A 25 batch. I didn't promise anything that I will finish the syllabus before this month. I didn't promise anything for 25 batch. Uh, right, but I'm doing everything here, Avni. Actually, I told you, I plan to stop the classes. I almost plan to stop the class for 25 batch because there was only one student came for physical class, right? Then I focus much for 26 batch. So then somehow she stayed. I don't know why she stayed until the last day. And then I said, okay, then at least for you until you do your A level, since you joined for my classes since from the beginning, it's okay. Only you also fine. I teach you, and because you came to my class, I'll teach you till your A levels. And because of that girl only, I continued this 25 class. It's almost I could have I should stop this batch. Then January onwards only we started this online class. I don't have any physical class for 25 batch. Then January onwards only. December end onwards only we start to work. Then January onwards only we started to plan that revision, this revision, this, that, and then now we are having around 50. The last few months, many students came. Right. So this 6 months, 7 months, I think I am doing my best. But I could not plan this 25 batch. Online classes, we can plan nicely and we can work. Physical classes, once a week only we want to do a class. On a poetry only, really only we have to put extra class. But online classes are not like that. Because the recording option is there. Whenever we have time, night time, we can do lots of sessions. So therefore, this 25 batch I could not plan properly. Could not plan means with the time we have limited, could not do. But 26 batch I am planning everything properly and I am doing right. So, but I am doing my best. You understand what is possible in my end. Every day, night. I think no one is doing like this. Yesterday, today, tomorrow, likewise, every day. So I'm doing everything impossible. But when you compare with 24 batch and 25 now, 25, the work that I am doing these days, when you compare 25, how the way that I work for my 24 batch and current the way that I'm working for my 25 batch, I am giving, I think, 300 to 400% than my 24 batch these days. I don't know how much we're getting the benefit, but let's do. We'll do. I have to do this. Right, okay. Session is finished. Then redo these questions again and sleep. Then have a nice day. Start up. Bye.